This is Nitin Dahad with the Times, and I'm speaking to Jim Tung, who's a fellow at MathWorks. Jim, hello.
Hello.
So, Jim, we're here at CES 2025, and a big theme right now in this hall is software-defined vehicles, and I think you have a very big play in some of that in terms of your products and what you've been doing over several years.
Well, thank you. In fact, our history with automotive goes back many, many years, in fact, decades.
Yeah.
And I think the interesting thing about software-defined vehicle is that it's the bringing together of two quite different communities, the system engineering communities and the software engineering communities, who are bringing more modern software development processes into it. It's an interesting time these days, however, because I think a lot of the OEMs, Tier 1s and Tier 2s, have invested to say, how can we improve software, but also, what are the new EE architectures? How do we move from dedicated ECUs to zonal computers to vehicle computers?
Yeah.
What functions should go where, and all those kinds of issues.
Yeah.
And then, how do I take software development talent and processes and make them work with the system engineering ones? And it's a really interesting challenge.
Yeah.
When we look at our history in looking at systems engineering is the V cycle, or the V model, where you start with a high-level systems description and requirements, you decompose it to the subsystems, decompose it to the components, implement the components, recompose them back into the subsystems, and recompose them to the systems, and then voila, you've got your system that you want. And that's the way a lot of automotive companies have thought traditionally.
Yeah.
Today, there's a need to move away from that perspective, because you really want to compress all these different things into one place, where you're looking at the system level and the scenarios for the vehicle. You're also looking at how components are going to behave along with the system, and being able to essentially compress and eliminate that V and make it all a playground, a joint playground, is one of the things that we see happening and we want to enable to happen. The other piece of it is how to leverage cloud.
Yeah.
Because you have different players who want to come together, you want to be able to virtualize and simulate more, and you want to be able to do it at scale.
Yeah.
Right?
But that's, we hear those and great words from everybody we speak to here, but there are big challenges, because I think there's one of the big problems might be just, like it's the old traditional hardware throwing something over to software, and things need to go backwards and forwards, but there's a new element with all this virtualization and the models and the twins. How can that all be made to work effectively?
Well, I think that's a great point, because I think in this hall, when people talk about virtualization, they're often talking about the virtualization of the ECUs, or the virtualization of the processors.
Yeah.
So if you're pre-silicon, or if you just don't want to have access to a hardware kit, how do you shift left in that V?
Yeah.
But here, what we're talking about is virtualizing everything.
Yeah.
Okay. It's virtualizing the system behavior, the scenarios, the cluster, instrument cluster, and the processor, in this case for a dedicated ECU, working with our partner Synopsys with their Silver tool. And so in fact, what we see with this type of environment is that it's bringing together lots of different pieces in a partner ecosystem. We have our capabilities, it's all running on AWS Cloud. We're working with Electrobit to provide the middleware. If you care about automotive, there are two architectures. One's called AUTOSAR, a classic, and then there's AUTOSAR Adaptive.
Okay.
And Electrobit provides the production middleware for both of those.
Okay.
And so we've worked with them. We develop the algorithms, given the context, automatically generate the code. The code gets integrated with the Electrobit middleware for either AUTOSAR Classic or Adaptive. And then if there's the need to represent the dedicated ECU, we bring in Synopsys Silver to represent the processor.
Okay.
Okay? And so virtualizing not just the processor or the ECU, but in fact everything, means that you can make the entire development process more compact, where it's much more of a place where you can say, how do I do a scrum?
Okay, yeah. But I think it's very different to what I think maybe in my world, or what I've always envisaged is, it's all this EDA players and the tools and whatever, but I think those are really at the sort of RTL level, and this is taking it much higher, isn't it?
It is. It does take it to a different level, but we've always also had integrations with the EDA players also.
Okay, yeah.
Okay, because MATLAB and Simulink have always had integrations where they either serve as the golden reference model, or they're provide, in which case it's an A/B comparison of the golden reference model versus a specific implementation.
Right. Okay.
Or we're providing the system context that the RTL description needs to plug into as part of the overall system.
Okay. Now, I'm going to talk to your colleague in a minute to get a quick demo.
Sure.
But before you go, what are the key things you've been hearing and seeing at CES here this week?
That's a great question. I think the thing we're hearing here is about how do I invest and how do I manage my risk?
Okay.
Okay, because I think a lot of the automotive companies have taken certain directions over the last number of years about how they want to proceed, but they're realizing that the decisions maybe aren't as clear cut as they might have thought. And so they need to look at, for example, if I'm looking at AUTOSAR Classic, AUTOSAR Adaptive, if I'm looking at what's going to go on a dedicated ECU versus on a zonal computer, they need some approach to be able to accelerate how they develop their software. That's a given regardless.
Yeah.
But to do it in a way that lets them have the freedom to target to an ECU, a dedicated ECU or a zonal computer, for example.
Yeah.
And so one of the things that we've done with the automatic code generation is to provide that insulation from those kinds of decisions.
Okay.
So you can have the model to say, here's the algorithm, then you can automatically generate code to whichever target you want automatically.
Well, Jim, thank you. I'm now going to talk to your colleague.
Please.
Hopefully we'll talk to you again soon.
Okay. Thank you very much.
Thank you. So I'm talking to Omkar Kave, who's going to give us a demonstration of some things that Jim was talking about. Omkar, hello.
Hi. So as Jim was saying, let's say I have a software feature that the customer wants, and the software feature can be delivered with a software change. I've set up a simulation where I've already done the software change. In the simulation, I have two vehicles. One of the vehicles has the feature, one of them doesn't. The one that has the features, I've taken the virtual ECUs and deployed them on the cloud, and I want to do a full test now.
Yep.
Those virtual clouds are in the loop with Simulink at the moment. So I'm going to continue the simulation, and I've put the vehicle in sports mode, and as one of the vehicles is in sports mode, that is going to take off, and it'll start accelerating, as you saw.
Yeah.
This whole test was done in the cloud. Simulation was done in the cloud, and you can do very large-scale testing with this sort of features. So yeah, this demonstrates how you can take something that you've developed locally, deploy it to cloud, test it out, deploy it to do a CI/CD, deploy.
And you've got the behavior, for example, in the Synopsys Silver tool.
Here in the Synopsys Silver, as soon as I put it in sports mode, the current requirements change from 300 to 500. And you're able to live record that.
And you can do a lot more environmental simulation then.
You can do as many simulations as you want with multiple different inputs to the simulation using Simulink.
Okay. Well, Omkar, thank you very much.
Thank you.